Hello and welcome, folks. So let's have a look at these two triangles here. We can take a look and see what we have. Notice what's going on here. We seem to have two triangles here, and I can go ahead and mark pieces of information. I've got two 60s here. They're both congruent. And I got two 70s here. So I've got another pair of angles here that appear to be congruent. So I got two pairs of congruent angles, and they appear to be in corresponding positions. Furthermore, the two 6s guarantee that I've got a pair of sides, and again, they appear to be in corresponding position here because they're both opposite the blue angles. So wait a minute, are these triangles congruent? Well, I mean, considering what's going on, some of you may argue, wait a minute, this is just angle, side, angle, right? Because I got two pairs of sides and a pair of angles. However, we have to be a little bit careful about this here, because as much as we like to call this angle, side, angle here, we note that something is very much the matter here. Notice how the pair of sides, these 6s here, happen to sort of not be in between, right? We mentioned in our first lesson here that when you're dealing with congruent triangles and angle, side, angle, you have to ensure that the angle is sandwiched in between the two sides. Here, our green side seems to have escaped the confines of the angles here and has gone off on its own. So we can't really do that here. Unfortunately, it seems like this is not angle, side, angle. Wait a minute, we can't despair about that here. There's got to be something else. Well, I mean, I think we could probably figure something out here, right? Because noticing that this is a triangle here, if this is 60 and this is 70, we know what angle C is, right? Because that's 180 minus 60 minus 70, and that's, I think, 50? So this angle is 50 here. In this triangle, we can do the same thing. This is 50 here. So I've got this black pair of angles, and wait a minute, now this slams the door on the side BC and EF here. Now BC and EF are sandwiched in between the two pairs of congruent corresponding angles. If we ignore A and D, if we ignore the blue angles here, we've got ourselves angle, side, angle, which is perfectly okay. So technically, even though it wasn't there, technically we did, even if we did not have angle, side, angle at the beginning, these two triangles still happen to be congruent to one another, which is great. But notice here that we actually didn't need the 50s here. We actually didn't need to go ahead and do this here. We could have just ignored the black angles and done a pair of blues, a pair of reds, and a pair of greens, and they all worked, right? So in this situation, this lends the existence of another way of proving triangles congruent, and this we're going to refer to as what is known as angle, side. So this is known as the angle, side theorem here. We can say that two triangles have two pairs of congruent corresponding angles, and a pair of congruent corresponding sides that are not between the angles, then the triangles are congruent here. So in this situation here, right, we can have this black pair of angles here. We can have this red pair of angles here. Now, in this case, for angle, side, it can be any side that's not AC or FD here, because if we pick AC and FD, those are the sides that are sandwiched in between the two pairs of congruent angles here, and that would just be angle, side, angle. So we can do something like, say, AB and ED here. So this is an example of angle, side. Note we call this a theorem here. We call this a theorem because of the fact that this exists as a result of, this is an offshoot of angle, side, angle, right? We know that this is true because angle, side, angle exists, okay? So considering this here, now that we have this sort of thing available to us, we can now go back and tackle a couple of other things here, right? So now we have this as another tool that we can use to prove that two triangles are congruent here, and angle, side will work out very easily. Now, let's go back here. You may recall yesterday in the previous lesson here, we proved this particular theorem. Two sides of a triangle are congruent, and the angles opposite them are congruent. We proved that very easily here using side here. Now, note that we can look at something known as the converse of the isosceles triangle theorem. Maybe this works in the opposite direction. So again, if you have a theorem, one of the things we can think about, does it go the other way? So now the converse is pretty easy, right? Because we had this as our original theorem here. If two sides of a triangle are congruent, the angles opposite them are congruent, all we're doing is just swapping the order. So now if two angles of a triangle are congruent, then the sides opposite them are congruent. And just like before, ladies and gentlemen, we're going to do this exactly the same way. We're going to prove this particular theorem to be true. So this should work out just as well. So yet again, we'll go ahead and sketch this out. Now, you may want to refer to your notes from yesterday, the previous lesson here, because you'll see that they work in very similar ways. So now we're given that two angles are congruent. So angle B is congruent to angle C here. And we want to prove that AB is congruent to AC, right? So now, you'll notice the tables have turned here. So this looks a lot like the proof, the setup for the proof that we did in the previous lesson here. You recall, this was what we did here. We were given AB is congruent to AC. We had to prove angle B is congruent to angle C. And now we're just doing it in reverse here. We're just going backwards. Okay? And it kind of makes sense considering that we're trying to find the converse here. Well, we have a lot of different options here. One thing that we can consider is, wait a minute, well, you know, if you recall in the previous lesson, we constructed an angle bisector. That worked so well, we might as well do it again. So let's go ahead and construct an angle bisector. So you'll note that just like before, we'll do the same thing here. And the structure of the proof is going to be very similar to the one we just looked at here. So yet again, we'll say construct a segment AD with D on BC such that AD bisects angle BAC here. This is true since each angle has a unique bisector. You'll notice that this statement here is identical to the statement that we did before, right? In this situation here. The opening of the proof is identical to the opening of the proof that we looked at previously, and it works just fine. There's nothing wrong with just doing this here, right? Because it worked so well before, let's do it again. Now, let's get back to our proof here. Now, we can basically go ahead and take that here. We can say that by definition, in this case, right, we know definition of angle bisector. Right? We can mark the angles now on top. Angle BAD is congruent to angle CAD here. Right? We're also given angle B is congruent to angle C. Right? That's also given here. And of course, the last thing we have here is this. AD is congruent to itself. By reflexive property, AD is congruent to itself. Thus, and now, notice that we have angle side here because, again, we see that the side AD has escaped the confines of the two pairs of angles that we have here, so we can put it all together. Thus, we can say by angle side, theorem, triangle BAD is congruent to triangle CAD here. So now we can just finish it off because remember, now we have corresponding sides. Therefore, AB is congruent to AC since, again, corresponding sides, or in this case, corresponding parts. It doesn't really matter what you want to say here. Corresponding parts of congruent triangles are congruent. And we are done. So as you can see here, this proof worked out really nicely. Again, it's very similar to the proof from yesterday here. You know, this is the kind of thing that where if you've got something that works, there's no need to really reinvent the wheel every time. You might as well just keep using it. So again, remember how I mentioned yesterday with this theorem here, you wanted to write the theorem out in full. Now that we know that the converse of the theorem works as well, you have to really make sure that we're using the theorem in the proper direction here. So again, this is why you need to write out this theorem in full. You can't just abbreviate, you can't call this the isosceles triangle theorem. Interestingly enough, if we go back to this actually does have a name. So this theorem here historically was known as the pons asinorum, which was a Latin phrase, and I'll talk about that in class. So in theory, you can call this pons asinorum here, but it's such an old term that's fallen out of favor, and very few people will know what you're talking about here. So let's avoid that sort of risk here. Write this theorem out. Same thing here, write this theorem out. Please make sure that you write it out here so that we all understand what's going on here and we can communicate properly.